Right, so let's talk about trigonometric functions, right? Take a look at this triangle to the right of the page here. This is a right triangle, we know this. And just a quick overview, right? This angle, this acute angle here is labeled by that symbol. This is a Greek letter. It's written as like a 0 with a horizontal bar through it. This is the Greek letter theta. Okay? It also, like phonetically, it makes that th sound, like thin. Okay? So that's the Greek letter theta, and it is the go-to symbol for angles. Right, so in a right triangle, usually we label one of the acute angles as theta and so on. Now, if you have your theta labeled where this is labeled, then we know that the longest side of the right triangle is always the hypotenuse, right? And it faces the 90-degree angle. And that leaves us with these other two sides. These are the two sides of the triangle that make up that 90-degree. They are called the legs of the triangle. And if you have theta defined where it is, one of the legs is always going to be touching that angle theta. Another word for touching is adjacent, right? So this is the adjacent side to theta. And here we have the opposite side to theta. So this is just, how we label the players of the game. Now, suppose just for fun that, this opposite side had a length of 1 in this triangle, and the hypotenuse had a length of 2 in this triangle. Now, if I were to ask you, what is the ratio of the opposite side of theta to the hypotenuse? What do you think? What's that ratio? It's 1 to 2, right? So what does that mean? That means if the opposite side had a length of, 7, how big would the hypotenuse be? 14. So it's just the ratio, right? The ratio is 1 to 2, okay? We might say 0.5, but we really understand it's just a ratio, 1 to 2. One is twice as big as the other, right? Now, this statement here, ratio of the opposite side of theta to the hypotenuse, that is a mouthful to say. And the Greeks knew that it was a mouthful. So you know what they did? They figured out a notation to just basically shorten that, to summarize that. So all of that, right, they called it sine of theta. Okay? And we abbreviate it even further as sine of theta. We don't call it sin. No, that's not a thing. It's sine of theta, right? And notice how you have to have the theta there, because that word sine, right, it's the ratio of the opposite side to the hypotenuse. But the opposite side of what angle? Theta or this other one? You need the theta there, okay? Right, and just like that, okay, they also came up with abbreviations for the ratio of the adjacent side to the hypotenuse and opposite side to the adjacent, and so on. You've seen this. You've known this as SOHCAHTOA. Well, now we know what it is. It's just ratios of the sides. So, talking about ratios, right? Which one here did we say which side is always the longest one? Hypotenuse. So if you have a ratio like this, opposite over hypotenuse, which of those, the numerator or the denominator, is always going to be bigger? The denominator. So what type of fraction is that going to be compared to 1? Greater than 1, less than 1, or equal to 1? Right. It's going to be less than 1 always. Well, what about the cosine? If it's adjacent to hypotenuse, is it going to be less than, greater than, or equal to 1 always? Less than 1 always. Okay, so let's talk about the tangent. The tangent compares the opposite side to the adjacent. Is there a condition as to which of those legs must be greater than the other? No. So the tangent can have any value. Can it have any value? Can these two legs be equal? Yes, so it can be 1. The ratio can be 1 to 1, or it could be 1 to 2, 2 to 1, whatever, okay? Now, if I compare the opposite to the hypotenuse, 1 to 2, I can also compare hypotenuse to opposite, 2 to 1, right? Well, when I do that, and I do hypotenuse to opposite, what would that ratio look like? Greater than 1. This one? Greater than 1. And this one? Any value. Okay? So these two are greater than 1, always. And this one is any value. Okay, so if you look at the sign, it's opposite over hypotenuse. And cosecant is hypotenuse over opposite. So we went from here to here. We took the reciprocal, right? Not the inverse. Please don't say inverse. Often students confuse the word inverse and reciprocal, right? That's cool if you're just, anybody. But like for a sophisticated math student, that's like not cool, right? So these are the reciprocals of this. And this is the reciprocal of this. That's why we call cosecant, secant, and cotangent reciprocal functions. All right? So if you go here, cosecant, secant, and cotangent are reciprocal functions. And reciprocal means 1 over. I can always write them like this. So cosecant is 1 over sine, reciprocal of the sine. Secant is 1 over cosine. Okay, if you get them confused, so look, you see how sine and cosine, one starts with an S, one starts with a C? The reciprocals get flipped. One starts with a C, right? The S starts with a C, the C starts with an S. That's how I remember them. I don't know. It's a Greek. It comes from the Greek root. So the sign in Greek is not sine, it's actually sinus, cosinus, and so it has to do with what the Greek words mean. But yeah, there's also other relationships later. Okay, tangent, right? Another relationship is tangent is also sine over cosine. And cotangent is cosine over sine. Okay? All right. So here, this is something that, you could have done in geometry. Basically, it says find the exact values of the 6 trig functions of theta. What do exact values mean?
Fractions.
Yeah? Fractions, roots, no decimals. Because 1/3 is 0.333333, right? So if I round 0.3, that's an approximation. The exact value is 1/3. Okay? All right. We want the trig functions of theta. So first thing you do, define theta as an angle. There it is. And now you want to identify the different sides. So the opposite, the adjacent, and then the hypotenuse. So sine of theta is what over what? Right? Opposite over hypotenuse. So here it would be
33 over 56.
65. Because it's over the hypotenuse. Cosine of theta is 56 over 65. Tangent of theta, 33 over 56. Okay? Opposite over adjacent. So now, cosecant, secant, yeah. They're just what?
65 over 56.
60, well, for this one, it's 65 over 33, right? Because cosecant is the reciprocal of the sine. And then 65 over 56 and 56 over 33. Okay? So that's like basically what the ratios mean. Okay. Now, let's get to some interesting problems. If the sine of theta is 1/3, Find the exact values of the remaining 5 trig functions of the acute angle theta. Okay, take a look at these two problems. Let's compare. In the first one, we had a triangle given to us and we had the sides laid out. Okay? In the second one, all I have is one of these ratios. In order to do the rest, I essentially have to recreate or create a triangle of my own. Okay? So, sine of theta is equal to 1/3 is what I have to go on, right? The first thing you want to do is draw a triangle. Okay. So take a look at a triangle. Here, I can draw a right triangle. And I'll label one of the angles theta. Okay. Let's take a look at what this ratio says. It says there is some mystery angle theta, the sine of which is 1/3. Now, sine, remember, was opposite over hypotenuse. So the opposite side to theta is 1, while the hypotenuse is 3. Okay? And then I need to find the missing angle x. I'm sorry, the missing side. Okay? So, Pythagorean theorem. Yes, go ahead.
I have a question.
Yeah.
You can do it first.
No, go ahead.
It's like for cosecant, would it be 3 or would it be 1/3? Or not like 3 over 1, it doesn't matter.
The cosecant?
Yeah, like you want it to be
3 is good enough. Yeah, 3 is good. Okay, so to find the missing side, it's 1 squared plus x squared equals 9, right? Pythagorean theorem. So x squared is equal to 8. Take a square root, take a square root. X is plus or minus root 8, but we can't have it be minus, right? So it's x is root 8. Okay, what's root 8? 2 root 2. Always simplify your roots. Okay? All right, now that we have all 3 sides, then the rest is kind of, just like what we did before, right? So sine we were given as 1/3. Cosine is 2 root 2 over 3. Tangent 1 over 2 root 2. Okay, let's think about this for a minute. What would you do here? You would want to, Andrew.
You want to get the root out of the denominator?
Right, you would want to rationalize the denominator, right? So let's think about this for a minute. Let's think about, do you guys know why we always have to rationalize the denominator? You've probably never asked because you've always been told by your math teachers and you've obediently just always rationalized the denominator, right? So that comes from the fact that before, in the old days, there were no calculators. So all these calculations had to be done by hand. There were tables or there were slide rules, right? That was like the old version of the calculators. It was a ruler with this bar that slides back and forth, and that's how you could add, subtract, multiply, and divide. Well, the thing is with the slide rule, you can only work with rational numbers. 1, 5, 1/2, 2/3, right? That's why we had to rationalize. But now, do we use slide rules now? We don't. Now we have calculators. So, it is no longer necessary for us to rationalize the denominator. So a few years back, the math department, we got together and we had a discussion and we decided that after Algebra 2 or Intermediate Algebra, we no longer are going to require students to rationalize the denominator.
Wow.
So, 1 over 2 root 2 will just stay as is. Now, I know in the beginning, you just have that urge, so you always just, mechanically go ahead and do it. That's totally fine, but you don't have to. Yeah.
This is a general about class. Thinking about calculators. Like, do you like calculators or like that?
Okay. Most of my quizzes or tests have 2 parts. a non-calculator and a calculator part. And then there are also some that have no calculator for the whole thing. So, yep, because, listen, I can teach anybody the keystrokes to solve a problem. That doesn't mean you've understood how to do the math, right? So you have to know, everything. Plus for the AP test, there's always two parts. Okay. All right. So here we go. Cosecant of theta is 3. Secant of theta is 3 over 2 root 2. Cotangent of theta is 2 root 2. Now, a little, disclaimer for the denominator there. 1 over 2 root 2 is totally fine. 1 over root 8, not fine, because it's the root isn't simplified, right? So root 8 is not okay, but 2 root 2 is totally fine. Okay.
Do you have like half credit stuff or?
I do. So if there is correct work shown, it may qualify as partial credit. Okay? All right. So, all right. Special triangles. So you know that there are two special triangles, right? The right triangles, the 30, 60, 90, and the 45, 45, 90. Okay. Since we've been talking about ratios of sides, now you know that trigonometry is basically just comparing sides, right? All right. In a 30, 60, 90 triangle, how many different sizes of angles are there? 3. And you've learned in geometry that big angles face bigger sides, smaller angles face smaller sides. So if there are 3 sizes of angles, there must be 3 sizes of sides as well. So here, if there is a small, medium, and large angle, then they face the small, medium, and large side. Okay? Well, we already knew that the hypotenuse was the largest side. That leaves the legs. Of the legs, one is the smaller leg, the shorter leg. The other one is the longer leg. Okay? So we're going to call this the short leg. And we're going to call this the long leg. Okay. Whatever the short leg is, here it's x. Remember, it's all about ratios. The long leg is root 3 times the short leg. So it's short times root 3. And then the hypotenuse is always short times 2. Okay? So, here we go. 30, 60, 90 triangle. Suppose my short side is 1 here. The short leg is 1. How big is the long leg? 1 times root 3, which is root 3. How big is the hypotenuse? 2. So, take a look at that angle, 30, okay? Would you be able to tell me what the sine of that angle 30 is based on that triangle?
Yeah.
What is it? 1 to 2, 1/2. Okay, suppose my triangle was different. Suppose this short leg was 7. How big is the long leg? 7 root 3. How big is the hypotenuse here? 14. Okay, so let's go back to this angle 30 now. What's the sine of 30? 7 over, which is what? Oh my God, it's 1/2 again. It's always a half. Because whenever you have a 30-degree angle, it comes from the 30, 60, 90 triangle. And if the ratio of the sides is always going to be so that the hypotenuse is twice the short leg, then there is no other way for it to look. Okay? So whether you're here, or whether you're in France, or whether you're in the southern hemisphere even, sine of 30 is always going to come from that triangle, and it's always going to be 1/2. Okay? Okay, same with the other ones, like cosine of 60, tangent of 30, whatever. Okay? So that's that. 45, 45, 90 triangle. How many different sizes for angles in this one? 2. So 2 different sizes of sides, which means the legs are equal to each other, and the hypotenuse is always the leg times root 2. Okay? So, if I have a triangle here, 45, 45, 90, okay? And one of the legs has a side of 3. How big is the other leg? And how big is the hypotenuse? 3 root 2. So, forget about sine, cosine, tangent. What is the ratio of the sizes of the 2 legs? What ratio do they have? 1-to-1 ratio, right? So, let's talk about this then. Tangent of 45. SOHCAHTOA, right? What's tangent? What over what? Opposite over adjacent. So if it's opposite over adjacent, what's the ratio? 1-to-1. So tangent of 45 is always 1, right? So that's one thing that if I was walking down the street and somebody taps me on the shoulder and like, what's tangent of 45? I'm like, 1-to-1 ratio, right? The legs are 1-to-1, okay? So that you need to know. Yes?
So then wouldn't sine and cosine also?
Yes, it would be the same, right? Because the sine is the ratio of the opposite to the hypotenuse. Cosine is the adjacent to the hypotenuse. So yes, they're the same. Okay? In fact, we're going to do that right now. So here we go. Without using a calculator, do this. So we need to find the cosecant of 30. By the time we're done with chapter 4, you'll just know them. But for now, right, let's just draw a triangle. That's a 30, 60, 90. And I can do this really quickly, right? And you will too. 1 root 3 and 2. Okay. Cosecant is what over what?
1 over sine.
Right? Or hypotenuse over opposite. I'll take a question in just a sec. So hypotenuse 2 over opposite 1. So that's 2. Okay, Ryan, question.
Is it always just a 1, 2, and root 3? Yeah.
Yeah. It's 1 root 3 and 2, right? Because that's where that comes from. Okay, the ratio, the sides in a right triangle in a 30, 60, 90. It's short leg, long leg, hypotenuse 1, root 3 and 2.
But is like the go-to like numbers to put on there just 1?
Yeah, because you know if you put like 5s, then when you divide, they're all gonna cancel out.
Oh, it's always going to end up.
It's always gonna end up as 2, right? It would have been like 5 to 10 or 6 to 12. And then they'll all cancel. So our go-to is always 1, root 3, or 2. Okay? All right. Sine of 45. Now we draw a 45, 45, 90. And again, my go-to is always 1s for the small sides. And then 1 times root 2. So what's the sine of 45 then?
1 over root 2.
1 over root 2. And the cosine would also have to be 1 over root 2. Okay. Now, without using a calculator, insert the appropriate symbol into each equation. We have to compare these two quantities, okay? See if they're equal or greater than or what. So, let's see. Tangent of 60, okay? So I need a triangle, which I already drew one. I don't need to redraw another triangle every time, right? Tangent of 60 is opposite over adjacent. So what would it be here?
Root 3 over 1.
Yes, sorry. Root 3 over 1. So root 3. What about cotangent of 30? Cotangent of 30, that's adjacent over opposite.
1 over root 3.
Is that right? 1 over root 3?
Oh, wait,
Root 3 over 1. So those two are equal to each other. Okay? All right, next. Cosine of 30. Again, you can just use that same triangle, right? Cosine of 30, adjacent over hypotenuse is what?
1 over 2. Oh, no, root 3 over 2.
Root 3 over 2. Okay, so let's see. 30 degrees, adjacent, root 3 over 2 hypotenuse. Okay, what about secant of 45? It's
1 over root 2.
hypotenuse over adjacent.
2 over 1.
Root 2 over 1, so just root 2. Okay, now, I don't have a calculator, but I need to compare these two. To compare, I don't necessarily need to know what their decimal approximations are. So let's look at this. We've got these roots, right? Let's talk about roots for a minute. We have root 1, root 2, root 3, root 4. Root 1 is 1. Root 4 is 2. That means root 2 and root 3 are within 1 and 2, right? And then root 3 is like, a little bit bigger. I don't care how much they are exactly, right? So now I'm comparing root 2 and root 3. Okay, so I know root 3 is a little bit bigger. Here I have root 3 divided by 2. So what do you think happens to that value?
Cuts in half.
It gets smaller than the root 2, right? So I know that this is smaller than the other one. See that? No calculator needed. It's not that type of problem, right? Okay. So, one more time, without using a calculator. So these would pretty much all be on a non-calculator section. Like these for sure on a non-calculator section. Like, example 3 and 4. Well, actually, none of the examples we did so far would ever be on a calculator section. Okay? All right. With that, okay, so this is a 45, 45, 90, right? So what do you think?
The sides can just equal each other.
The sides are just equal to each other, right? Because the legs have to be congruent. So x squared plus 4 is 6x minus 5. And then it's a quadratic equation, so move everything to the same side. Set it equal to 0. Okay? That's why you learn, chapter 4 and 5 in algebra 2. And now, factor x minus 3 squared equals 0. So x is 3. Okay? Questions? Okay. Now, solving right triangles. So take a look at this problem. A competitor is swimming in the swimming portion of a race, and they are swimming along this course X, right? You have to find the distance that he must swim in order to reach the shore. So basically, we have to find X. So what we're shown here is a picture, right? And what you want to do is you want to isolate from that a mathematical diagram, right? Picture's cute, okay? But all you need is the mathematical diagram, all right? So look at what we have here. You're given the 90-degree angle, and that's what you go on. You have a 90-degree angle. You're given one angle, and you need to find a side. Well, that has trigonometry written all over it. So immediately you think, okay, it's got to be sine, cosine, tangent, one of those ratios. So how do you decide which one? You have to figure out what your players are. What are the key players in this problem? Well, I'm given an angle, right? And I'm given two sides. So in comparison to that angle, or in reference to that angle, What is the 75-foot side? Is that adjacent, opposite, or hypotenuse? Adjacent. And this is opposite. Right? So that tells me this is what ratio? Tangent. So, tangent of an angle. Remember? It's the ratio of the, opposite of something. So, tangent of 48 is equal to opposite over adjacent. And that's my mathematical equation. Now all I need to do is solve it. And I rely on my algebra knowledge to solve that. Multiply both sides by what? 75. Okay, so go ahead and take out your calculators. X here is 75 tangent of 48. 75. Tangent is in the trig menu. And you can just go ahead and find tangent, 48, enter. Okay. So this is 83.295. On tests and quizzes, I will have specified what decimal place you need to go to. And in preparing for AP, you have to have your answer given in the correct decimal places. Yes, it's points. Okay. On the AP calculus test, if you don't have it in the correct amount of decimal places, they will not give you credit for your answer at all. Like, no credit. 0 out of 1 points. Yeah. But you know what? By then, they're assuming you are a specific type of student. And my Precalc honors class is the same thing. I just assume that what I have in front of me is a specific type of student, right? Okay. So right now, if I haven't specified, then it's up to you. So I would say X is approximately 83.296, or we could say, that's approximately 83 feet. Okay.
How would AP want the answer to be?
AP always goes up to three decimal places. It's a given. Okay. Now, in this problem, we had to look for an angle. For a side. But if we have to find an angle, then we use the inverse trig functions. And the inverse trig functions are inverse sine, inverse cosine, inverse tangent. Okay? Okay. So take a look at here, this problem. It says to solve a triangle. Okay. Solve a triangle means find everything that's missing. At the end of the day, you have to have all three sides on all three angles. To start, you have to be given 3 pieces of information, and then you have to find the missing 3. So here, what is it that we have missing? Capital H is missing. That's the angle. And then remember from geometry, the way we label triangles is if you have a capital H angle, angles are in capital letters. Their opposite sides are given the same name but in lowercase. So capital H, capital G, little g, right? So little h is also missing and little f is also missing. Okay. One angle given, another angle given. I can find that other angle, right? Capital H. That's just 90 minus 41.4, and that's 48.6. Okay, now let's find little h. Okay, it's up to you which one you want to find first. All right, let's see what we have given. I'm given an angle. I like to work with information they've given me in case I made a mistake. Sometimes you have no choice, but when you do, you might as well. So I need to find h. I'm given that angle, and I'm given this side, 28. Yep. So this is the hypotenuse, and this is which side? The adjacent side. So this is which ratio? Cosine. Cosine of 41.4 is adjacent h over opposite 28. And then you do the same thing, multiply by 28. So h is 28. Cosine 41.4. Okay. And that is 21.0. Okay. So for the other one, you kind of reset. F is now opposite and hypotenuse, right? So we're going to do sine of 41.4 is opposite F over 28. And then, so F is 28 times sine of 41.4. And I believe that's 18.5. Okay. All right.